Are you hearing me? Yes. So, hello everyone. I'm glad to be here today at Ekoparty, and welcome for this presentation about some vulnerability research on the Gecko bootloader platform. So, let me start by introducing myself. Who am I? My name is Sami. I am working at a French security company called Quarks Lab as a security researcher, and I also conducted this research with another one of my colleagues, Benoit. Sadly, Benoit couldn't be here today with us because he's currently presenting the same talk on the other part of the planet at Hardware.io in the Netherlands. So we would both like to thank this conference for accepting our talks. And now let's dive into the main topic of this presentation, which is the goal of our research. So we choose the Gecko bootloader platform because it's one of the key components of Silicon Labs device, which is chip manufacturers. They are widely used across many devices, including the Amazon Sidewalk device, also the Freebox Delta and the security module, which is for the French internet boxes. You probably don't know it, but in France we do. And these chipsets are divided in two families. There is the EFR1 and the EFM1. The EFR device the EFM device doesn't have any radio capabilities, whereas the EFR does. They support many wireless protocols, such as the Zigbee or the BLE. And in our case, we will focus on two features of these chips, the update mechanism, which is the OTA, and the radio abstraction layer, which is implemented as a library called Rail. So let's begin to speak about how these chips are working. So they are based on ARM Cortex M33 processors, which implement all kinds of modern security features, such as the trust zone or the DSP. They obviously have some internal flash memory to store the code, as well as some RAM memory for the runtime application. And the way they interact with the rest of the world is by using hardware peripherals. So hardware peripherals are components that implement the features. It can be, for example, a clock, a UART, a radio antenna. And the way you interact with these components is by writing or reading at a specific address in memory. So this means that when you are trying to reverse this application or just look at the code, you need to have a clear understanding of the memory mapping to know what the operations the chip is doing. So here on the left, you have like the memory mapping, which starts at the address 0 with the bootloader. Then there is the application, and the higher addresses are reserved for the peripheral. So these chips are specially made to communicate over wireless protocols such as Bluetooth Low Energy. So let's speak a bit about it. Bluetooth Low Energy, or BLE for short, is one of the most used IoT wireless protocols. You basically find it everywhere in your smartwatch, in your car. Even these badges have some kind of BLE features. And unlike, this is not the same protocols as the classic Bluetooth, which focus on transmitting data, while the BLE protocols prioritize the power efficiency consumption. It allows your microcontroller to go into sleep mode as many times as possible when it's not processing data. So this way you can increase the longevity of your battery. In some device, you will find both protocols. For example, in the wireless speakers, let's say that you want to listen to, I don't know, one of your music, your favorite music. Like this one. Basically, what will happen is that your phone will send your music over Bluetooth, while you still can request the percentage of battery over BLE. So if we focus on the stack that is right here, you will see that there is two main parts. There is the host layer on top and the controller layers. So they can be located on the same device or in two separate ones. It doesn't matter. And this is what happens when you use, for example, a BLE dongle. Your computer will run the host layer, and the dongle itself will run the controller layer. And in this case, they will exchange some information using the HCI layer, which is just an interface layer for the two parts. So it starts, for the host layer, it starts with the L2 cap layer, which is just a network abstraction layers, because you can have different protocols above, but I will only describe the ones that are used on the chip. Then you have the ATT layer, which defines how the data are actually exposed. And on top of it, there is the GATT layer, which defines the client and server model for the protocols. Sorry, I messed up with my notes. So for the controller part, there is the link layer, which provide a bunch of quality of life services for the upper layers. Basically, that this layer will handle like the encryption, the CLC checking, and everything. And then at the bottom layer, there is the physical layer, which handles the modulation and the demodulation of the radio signals. That's this layer that will convert the analog signal received by the antenna to a bunch of bytes. So from a higher perspective, BLE works by exposing a series of services, and each services will have some characteristic which you can read, write, or ask to be notified on. So I hope with this quick presentation you are now all experts in BLE. So let's focus a bit about how these chips are updating. So basically, Silicon Labs implemented what is called an over-the-air update in their SDK. You can think about it as an update through any communication protocols. It can be UART, serial, BLE, or Ethernet. It doesn't matter. Most of the time, it's through wireless protocol because this is more practical for the user. And it allows updates to be distributed at a large scale. It obviously reduces the cost of delivering those updates and increase the rate of adoption. This is because manufacturers can make new firmware update available through their website or their Android application, and the end user will just download it himself or using the application to update his device. So talking about security, to handle this update, Silicon Labs created their own custom file format, which is called the GBL file format, which implement like modern security features such as the encryption or the signatures. But before going too deep into the details, let's first see a quick example on how you can, as an end user, update your device. So the first thing to do is to install the EFR Connect application made by Silicon Labs. Then you obviously need to use this application to update your device by sending the GBL file. And by doing so, you realize that the application doesn't work. Oh, fuck, it really doesn't work. So what can we do? The thing we can do is trying to reverse the application to understand what protocol it is using and why it fails, and then implement a script that will do the upload for us. So how this script will work, it's important to first note that the protocol I'm about to describe is the default protocol made by Silicon Labs in their SDK. Programmers can keep it or implement their own. It depends. And the way it works is that the chip will expose an additional services with two characteristics, the OTA data in blue and the OTA control in green. So by default, the chip is running the main application and waits for a signal on the on the OTA control characteristic. Whenever it receives a 0, it will reset in a mode that is called the data firmware upgrade mode, DFU for short. And once in this mode, it will do nothing except waiting for another 0. Whenever it receives it, it will go into what we called the update mode. And in this mode, you can send your GBL file as chunks because the BLE packet size are really small, so you need to split your file, send it chunk by chunk, and when you're done, you can write free on the control characteristic to signify that the update ends. And then the chip will perform some verification to see if the file is correct. So that's about it for the update. Now let's speak about how the file look like. So this is the GBL file format. It's composed of a set of tags, and each tag is made by a type, a length, and a value. So the type is like a magic byte that identifies it. Then there is a length field that defines the size of the remaining data. So these tags vary in nature. You can have mandatory one, optional one. Some can occur multiple times. It depends on the type of the tags. So every GBL file must start with a header file. This is mandatory. Then you can have any of these blue tags. They are optional, but if you want to use them, you must follow this order. For example, if you want to encrypt your file, you need to use the encryption init tag here, and then the rest of your file will be encrypted using AES. You can also add an application tag, a secure element tag, or a bootloader tag if you want. And then you need to provide the code of the firmware inside the program tag here. So this is the ARM instruction that will run. If you set the encryption, you must use the encrypted data tag instead of the program one. Then you can also add, for example, a certificate, signatures, and you must end your file with the end tag. So that's about it for the file format itself. Now let's see how the chip will parse it. So the parser for the GBL file is implemented as a state machine that starts into the init mode here in blue. And it will wait for, it will try to parse a header tag, and if it's valid, it will then go into the idle mode. And once in this mode, it will parse any tag as long as they are valid and come in the right order. So if for any reason one of these conditions is not met, it will go into the error mode here and stay in this mode during the rest of the update. So for example, if the parser parses a bootloader tag, like this, it will process the data contained in this tag and then go back to the idle mode. And once all the tags have been parsed, if everything goes well, it will parse the ending tag and then perform some verification to see if the file is correct. So parsers like these are often prone to errors and bugs, so we decided to look for vulnerabilities inside of it. And how did we do that? We used a fuzzing-oriented approach. Why, you may ask? Because first of all, it's an automatic and efficient way of looking for bugs. Moreover, there are a lot of fuzzing experts at Quarks Lab. And it was mainly for learning purpose, as the work I'm presenting today it was my internship work. So what do we need to run our fuzzer? We need to be able to first emulate the instruction, emulate the code that runs on the target, because the code is not meant to be run on our computer. Then we also need to be able to generate some interesting input for our fuzzer. And last but not least, we need to choose from the many available fuzzer online. And for that, we choose to use AFL++, as it's very simple to use. So talking about fuzzer, let's first talk about how fuzzing typically works. So this is an overview of the fuzzing process. You need to start by investigating for the entry point you want to test in your code. So generally, it will be a function that you want to test. Sorry. Once you identify the function you want to test, you need to select a mutation strategy. So how you will mutate the input given by the fuzzer. And AFL++ comes with a lot of pre-existing ones, but you can also create your own. And after that, you need to give a set of examples to your fuzzer, which will help him to understand what the input should look like and how we can process them. After that, there is the harnessing part. That's the part where you need to write some code that will interface between the fuzzer and the code you want to fuzz. And in our case, that's where the emulation will take part. And after this step, you can actually start to fuzz. So you need to, after each fuzzing session, you need to identify the potential crash found by the fuzzer, but also tweaks some parameters, let's say for performing reason, or maybe because there was a crash inside your harness, so you need to fix it. And you need to loop over these 3 steps over and over and over until you find a crash that is interesting for you. So I already talked about the attack surface. We want to fuzz the code of the parser. So let's see how we can mutate some inputs. So as I said, AFL++ offers the possibility to create custom mutators that can be used to get more control over the mutation. So the mutator we created takes an input given by AFL. We'll then apply a mutation that we create on it with some randomness, and then give it back to the fuzzer to test it. We also use the protocol buffers because it's an efficient way of serializing and deserializing the input in a fast way. And also it was easy to define the message type, as you can see here. So moving on to the harness part. As I said, because the code is compiled for the ARM architecture, we cannot run it on our computer. So for that, we need to use some emulation. And that's why we use Unicorn, which is an emulation framework based on QEMU, which is fairly easy to do and has a good integration with AFL++. So the first thing we needed to do was actually to map all the required memory, such as the stack or the application. And then we also had to patch a lot of part of the code because some part of the parser tries to access low-level peripherals that doesn't exist in the emulator, so it will make Unicorn crash. So instead, what we can do is use the hook features of Unicorns to replace those problematic functions with some Python code. So here, for example, we switch the classic memcopy with some Python code. This was mainly for performance reason, as it is more fast, sorry. And we also replace, for example, the SHA function to avoid crashes. So now we complete all the required steps, we can start to fuzz. So after multiple fuzzing comparing for about 10 hours, which is surprisingly not that much, AFL++ found 4 crashes. The 2 first crashes are false positive. These are crashes that happens in our harness, so it's our bugs, not the bugs of the emulated code. The last one couldn't be reproduced on the real target, so maybe because there are some checks that come before the part we emulated, but the last one is very promising. And in fact, it allows to discover that there was a buffer overflow inside one of the functions that is parsing the application tag info. So it's very simple. You have a buffer here located on the stack in red, and this buffer is given to a function that will copy the byte from the input variable to the buffer, but instead of checking for the maximum size of the buffer, which is this macro, it checks for the length set in the tag. So, and as an attacker, we can control this value. So it's pretty easy to set a very big value. And this way, we can create an overflow and overflow the return pointer of the function and gain control and then control over the code that is executed. So let me show you a quick demo of the exploit. If I found my mouse, yeah, right here. So on the left here, you have a code that will first flash a secure bootloader that with some keys that will only accept a sign update file. And then on the right, we are scanning for BLE devices and showing that there is a devices here that is named OTA with this MAC address. So now we can start the real exploit, which comes in 2 parts. The first part, we trigger the OTA to send a lot of data. We actually speed up a lot of this part because it was very long. The chip will send an error and reboots. We trigger the OTA once again, but this time we send the second part of our exploit. And now if we look for the BLE device around, once again, we should see here that there is not a new device, but a device named Pawn with the same MAC address. So this demonstrates that we gain control over the code that is being executed on the target. So now let me dig into the detail of this exploit. Sorry. Okay. So first, let me talk about the limitation we faced for the exploit. So the first thing is that if the encryption is enabled, we cannot exploit the chip because everything we will send will be first decrypted using AES, and it will scramble everything. The second thing is that if we want to send, for example, a shellcode, it needs to be small because of the BLE packet size. And the last thing is that we can try to write on the flash, since we can control the code executed. But in order to write on the flash, you need to erase the page first. And if we do that, some of the page crash and it will break the device. And that's happened a few times, so that's why you need to have spare one. But there is two things we can do. We can erase one page and write on it one page that is at this address, and this is the page where the main function is located. And the second thing we can do is that everything we wrote on the flash, even if it's not valid, even if it's not a correct GBL file, it will stay on the flash because the area of the flash is not wiped after the update. So on the left, you have an example of the content of the flash. You have the existing bootloader, which is running all the security features of the chip. So we start our exploit by triggering the OTA once to send a bunch of nopes instruction. Then we send a branch instruction. So this is the equivalent of a jump instruction in 86. And this instruction will jump to the main function, but not the one of the existing bootloader, the one of the bootloader we will send just after. So this is the rogue bootloader. It's not a signer or anything, and it must be compiled to run at this base address, but it's fairly easy to do. You just have to tweak some values in the make files. And after that, we can finally send our shellcode. So that's it for the first OTA. The chip will parse this file and check if it's correct. Obviously, it's not. So it will write some byte at the start of the memory, but we don't care. We trigger the OTA once again, but this time we use the buffer overflow vulnerability we found earlier to redirect the code execution to our shellcode. And this shellcode will erase the page at main and then copy the nopes instruction and the branch. So now every time the chip is rebooting, it will try to execute the main function, but instead it will execute a bunch of nopes, then the branch instruction, and then the bootloader we wanted to run. So that's how we point the board. So let's talk a bit about the impact of this exploit. So first of all, this vulnerability impacts all the devices made by Silicon Labs, both the old one and the new one. It can be triggered on any device as long as you know how to trigger the OTA. And by default on most of the BLE devices, there is no authentication. So an attacker can just connect to your device and try to exploit it. So when we see that we get a big score on the CVE, we were very happy. But then we realized that this exploit needs the OTA to be enabled. And what if it's not the case? So we decided to try to find vulnerabilities inside a component that will be used on all the devices. And that's the case for the radio library, Rail, which is present on all the devices and implement the software at the physical layer. So as I said, as I mentioned earlier, Rail is a closed source and obfuscated library made by Silicon Labs. It handles all the low-level operation of the radio for the programmers. And sorry. Yeah, it handles all the low-level operation for the programmers. So why do we want to look for vulnerabilities? As I said, it's a key component of Silicon Labs product. It's everywhere, and since it's obfuscated, there is no alternative to it. Nobody was able to provide something else, so it runs on all the devices. And if we find the vulnerabilities in this layer, it will bypass all the possible mitigation of the above layers. So how can we search for vulnerabilities? We can do two things. First, we can do some static analysis with some reverse engineering, trying to search for leaks on internet, for example. And then we can also do some dynamic analysis by attaching a debugger, for example. So for the static part, here is an example of the code you get from the Ghidra decompiler when you open the library. It's a fucking mess, let's be honest. And even making the difference between the name of the function and the name of the variable is hard. And on top of that, there is some undocumented peripherals that you can see here that we don't know about. So the first thing we did was actually to look on internet for some information about this peripheral. And we found some, both on internet and in some hidden Python code inside the IDE of Silicon Labs. And using all those information, we were able to create a Ghidra loader that maps some of the peripherals. And now we know that this function is trying to set some registers inside the radio controller. So if we continue this over and over, and after a lot of hours spending into reversing, you end up with this. So this is an overview of the architecture of Rail that we were able to identify. It starts with the public API that programmer can use in their code. So this API is provided as a header file, a .h. And the way it works is that you must first initialize the library using the Rail init function. So this function, under the hood, will set up all the required memory, set up some hardware peripherals, register some callback, and create the main event loop that will process the packet. And then, once the packet is received, some hardware peripherals may trigger what is called an IRQ, so an interrupt handler. And this interrupt handler will take the data, the current data they are handling, and copy them over some buffer in RAM, some global buffer, which can then later be accessed by the event callback. So this callback is the core of the Rail library. It is called periodically to process any available data, and it manipulates the packet data over a synchronized queue that the higher level protocols can use, for example, for sending or receiving packets. So that's about it for the architecture. Now we know we have a better understanding on how Rail works. We can move on to the dynamic analysis part. So for this part, we need to be able to do two things. We want to be able to send any kind of packet, even the malformed one, to the chip to see if it's correctly parsed. And we also need to be able to attach a debugger to trace the instructions that are being executed, and also dump some internal state of the library. However, this approach comes with some limitation. The first thing is that most of the time, it's not possible to send any packet using your computer. Your driver will just refuse to do so. And the second problem is that it's not possible to attach a debugger to the chip because it slows it down too much and prevents most of the device to connect to it. So you must say, okay, this is fucked up, we cannot continue our research, but there is hope, my friend. The first thing we can do is use a cool framework that is made by one of my colleagues at Quartz Lab, Damien, with the help of Romain Kerr. And this framework, which is called WAD, provides an abstraction for the radio hacking script. Basically, you can create a very simple script that performs some attacks such as hijacking or jamming in only a few lines of Python, and it will run on any hardware that supports WAD. So it's very easy for you because you don't have to worry about which hardware you have at home and all the firmware issue that you can have. And the way it works is that WAD will come in two parts. There is the host layer that are implemented from scratch in Python that runs on your computer, and this part of the stack will forward messages over the serial using the protobuf definition to the WAD device. And this device will, on its own, implement the controller layers. So for this part, we choose to use an NRF52 as our WAD device because it only costs like $5 and can send any kind of packets, so it was perfect for our needs. And now that we fixed the first problem, let's see how we can monitor the chip without attaching a debugger. So what we can do, instead of using a debugger, we choose to develop a very basic DBI, dynamic binary instrumentation tool, that will inject all the code for the debugging inside the application instead of having an external debugger. And by doing so, we were able to greatly increase the performance because there is no more back and forth between an external debugger and the chip. And this way we can actually connect using WAD. So by using the DBI, we were able to first monitor the behavior of the chip and also change it by, for example, changing the return value of some function. So let's see how it works under the hood. The first thing is that since Rail is a precompiled library, this means that it's an archive file with a lot of object files, so intermediate compilation file. So if we want to modify such file, we need to modify them at a binary level. And for that, we choose to use a Python package that is called leaf to do so. So the basic idea is that we will first open the library, extract all the object file inside of it, then look for the function we want to hook, and then add some debug code inside the function, repack everything to a new library, and then continue the compilation toolchain and continue the compilation toolchain. So on the right here, you have a basic example with a function here that is named foo, which calls an external function puts with hi as first argument. So this function will say hi to you. And there is also another piece of information that is added in the file. This is the relocation here in blue. This is an indication for the compiler to tell him that since we don't know the address of puts in this file, we want the compiler to change this instruction for a branch to the address of puts, for the real address of puts when he will link all the objects together. So let's say that we want to inject some code inside of foo, the first thing to do is to actually make some space for it. Then we need to move all the existing relocation to point to the correct place. And then we will add some code in purple that will first save all the current context of the function. So we purchase all the registers on the stack. Then we will call a function that is named dbi hook. So that's the function that will print the name of the function that is executed on serial. And once this function returns, we will restore the context of the function by popping all the registers, and then we can continue the execution. And we also need to add another relocation to the function dbi hook. And this way, we are able to define this function in another file, like a C file, which is very easier to do than programming it in assembly. So maybe time for a little demo. So here I choose to hook a function that is named HTI writeRxData that will print all the data received by this function on the serial. So now, if we scan for BLE device, we should see here that there is a device named OTA, like before. We can try to connect to it. And if we do so, you can see here that there is a lot of prints on the serial. This is because your computer is sending some packets to discover what are the available services. And here I'm also showing that if we read a characteristic, there is also a print on the serial. So that's about it for the demonstration. You must think we found a lot of cool vulnerabilities with those tools. Well, no, we didn't find any vulnerabilities for now because we didn't have the time, and this is still a work in progress. I guess that's research. Sometimes you found, sometimes you don't. But I think we still show a lot of interesting ideas and approach that you can use. And to conclude this presentation, we demonstrate how we can bypass the secure boot of Silicon Labs product using classical vulnerabilities. We also show that fuzzing is not hard. Like if I manage to do it, you can do so. It just takes some time. And we also shown a unique approach to the DBI that I didn't see anywhere else. So in my opinion, it will be interesting to dig deeper with this method. If for any reason you want some details on the exploit that I didn't present in this presentation, you can go to our blog post. And I will conclude by saying that I strongly encourage every one of you to open any embedded device that you may have, because you may find some cool vulnerabilities inside of it. So that's about it for the presentation. Thank you. And if you have questions, I can answer them now.
Hello. Yes. A question about the last part where you hook a rail. You overwrite the start of the function with your instructions. Did you try to just override the pointer to that PLT-like section, or doesn't work?
To the PLT section?
Yes, because you're pointing there that when the symbol is not resolved, you have a section that has a pointer to the function, right? So couldn't you just override the pointer to your hook instead of the original function, instead of overriding the function with instructions?
Yeah, that's the first thing we did, and it didn't work because it was not supported by the library we were using. The Leaf library just crashed if you try to do so. So I end up with this approach, which at least works.
Okay, thanks.
Any question?
¿Alguien más? ¿Una consulta? Bueno, despedimos a Sami con un fuerte aplauso, por favor. Y en 15 minutos retomamos la siguiente charla.